Hello everyone, I'm Baojing Huang. The presentation is Implicit Identity-Driven Deepfake Face Swapping Detection. I will introduce our motivation, contribution, and method, and then give the comparative experimental results of our work and previous work. For the deepfake face swapping, the target face is replaced by the source face through face swapping to generate a fake face. In appearance, the fake face looks like the source face instead of the target face. We resolve the general face recognition model cause face to obtain the explicit distance of these faces. Particularly, since the fake face is synthesized from the source face and the target face, we aim to explore an implicit face recognition model that can mine the corresponding target face identity based on the fake face. With the similarity between explicit and implicit embeddings of the given face, we can significantly distinguish it as real and fake, which facilitates forgery detection. In brief, the main contributions are as follows. From a completely new perspective, we propose the implicit identity-driven framework for face swapping detection, which explores the implicit identity of fake faces. This enhances the deep network to distinguish fake faces with unknown manipulations. We specially design explicit identity contrast (EIC) loss and the implicit identity exploration (IIE) loss. EIC aims to pull real samples closer to the explicit identities and push fake samples away from the explicit identities. IIE is margin-based and guides fake faces with known target identities to have small intra-class distances and larger inner-class distances. Extensive experiments and visualizations demonstrate the superiority of our method over the state-of-the-art approaches. We introduce the outline of our proposed implicit identity-driven framework for deepfake face swapping detection. We hybridize real face samples and fake face samples as training set. It's worth noting that we label the identity of the fake face with the corresponding target face identity. During training, we employ the generic face recognition model to obtain the explicit identity embedding of training sample as a contrast. The implicit identity embedding extracted by the backbone is supervised by the implicit identity exploration loss. Besides, real samples are pulled closer to the explicit identities, while fake samples are pushed away from the explicit identities. The difference between the implicit and explicit identities of face sample is guided by the binary cross-entropy to output predicted confidence. Since the fake face is derived from the source and the target face, we argue that the fake face contains more or less the identity information of the target face. As such, we propose to use the explicit identity of the face as a contrast to enlarge the difference between the real and fake samples in the feature space. Following the characteristics of our proposed implicit identity, the implicit identity of a real face needs to be consistent with its corresponding explicit identity, while the fake face is just the opposite. To this end, we adopt explicit identities as contrasts to initially guide the representation of implicit identities. The aforementioned EIC loss enlarges the difference between the real and fake samples in the feature space. At this point, the fake samples are only distinguished from the explicit identities in the feature space. To further clarify the implicit identities of fake samples, we design an implicit identity exploration loss, which uses the target face as a guide to refine the implicit identities of fake faces. In particular, for fake samples with unknown target faces and originating from the same video, we maintain their identity consistency to ensure that there is no large detection difference between the frames of the same video during face swapping detection. To comprehensively cover the actual situation, we take the fake samples of unknown target faces into consideration. The key idea is to maintain the identity consistency of frames in the same fake video. Since our proposed framework is composed of several collaborative components, including the EIC loss and IIE loss, we conduct ablation experiments on celebrity deepfake and DFDC datasets to verify the effects of these strategies. Cross-dataset evaluation results of the above models are tabulated in Table 2. From the table, we can see that our proposed IID generally outperforms our counterparts on unseen test data, even achieving significant improvements on some datasets. These gains mainly benefit our proposed IID framework, which learns the implicit identities of real and fake samples under the guidance of EIC and IIE. It is worth noting that our model is not the most superior on the intra-testing dataset. That's because our IID focuses more on exploring generalization differences between real and fake samples rather than simply fitting the training data distribution. We further conduct experiments across manipulation methods to further explore the generalization ability of the model for different manipulation methods. In practice, it's usually necessary to train on multiple manipulated datasets and tested on unknown samples. To demonstrate the effectiveness of our model in this multi-source manipulation scenario, we conduct experiments on the benchmark proposed by Sun. To visualize the effectiveness of our proposed EIC, we conduct visualization analysis on Face Forensics++ and Face Shifter. The cosine similarity between explicit and implicit identities serves as the explicit-implicit identity similarity EIIS for such images. For the pre-processed deepfakes of Face Forensics++ and Face Shifter video frames, we calculate the EIIS for each face image in them according to the above method. Overall, real and fake faces have a distinct boundary in terms of EIIS. Specifically, the EIIS of fake faces is about negative 0.3 to 0.5, while the EIIS of real faces is about 0.5 to 1.0. Note that there are still some samples that are obfuscated, especially for Face Shifter, as is across datasets. The cosine distance of each pair of face features is used as their identity similarity. We observe that positive sample pairs and negative sample pairs are distinguishable in terms of cosine similarity. Moreover, the distribution variance of positive samples is significantly smaller than that of negative samples, which implies that the implicit identities we extract are relatively stable. The results explain the effectiveness of our IID from the implicit identity perspective. If you have any questions or concerns, please do not hesitate to email me.